Hello, everybody. Welcome to this robotics seminar series implementation sponsored by Lockheed Martin. Today, we have the great pleasure of receiving Dr. Feng, who is an assistant professor at the Department of Computer Science and the Department of Engineering Systems and Environment at the University of Virginia. Previously, she was a postdoctoral fellow at the University of Pennsylvania and received her PhD in computer science from the University of Oxford. Her research focuses on assuring the safety and trustworthiness of cyber-physical systems, spanning many different applications domain, from autonomous robots to smart cities, medical devices. She's a recipient of an NSF Career Award. And with that, I will pass the floor to Dr. Feng.
Thank you for the introduction. It's a great honor to be here talk about my work about towards safe and trustworthy cyber-physical systems. So the first, what are cyber-physical systems? I'm sure many of you are familiar with the concept. Cyber-physical systems involve a collection of computing devices connecting with each other and communicating with interacting with the physical world via sensors and actuators. And increasingly, such systems are everywhere in our daily life, from self-driving cars to robots to smart cities to smart healthcare. It's estimated that the potential economic impact of cyber-physical systems will reach as much as 11 trillion per year by 2025. With our growing reliance on cyber-physical systems, it's important to assure their safety and trustworthiness. We are all hearing from the news stories, like a couple of years ago, a factory worker was killed in Germany by a robot accident. And early this year, a robot collision in a grocery store warehouse in UK caused a fire, caused significant economic loss. And early this month, the full self-driving car mode of Tesla was in California. It took control of a car and forced a very unsafe lane changing. The NHTSA is currently investigating the driver's claim. And we know a couple of years ago, the first incident of a pedestrian actually killed by self-driving cars. So we can see from all these news stories tells us the current cyber-physical systems are not so safe and trustworthiness. And these tragic incidents not only lead to catastrophic outcomes, but somehow it will decrease people's trust in CPS. So what are the challenges of assuring the safety and the trustworthiness of these systems? I think although we can have cyber-physical systems in many different application domains, they do actually share some common characteristics. So first, we know many cyber-physical systems, they collaborate or interact with human operators to harness complementary strengths of humans and autonomy. However, the uncertainty of human interaction or user errors could lead to safety hazards. Second, AI and machine learning techniques are increasingly embedded in cyber-physical systems. How can we guarantee their safety and the trustworthiness of these AI-enabled CPS? And lastly, many cyber-physical system applications are large-scale systems with many networked devices and components, such as swarm robots, the Internet of Things, or smart cities. The scalability is a big challenge for traditional safety methods, such as formal methods. So in today's talk, I'd like to tell you some of my group's recent works to address these challenges. Let's first talk about the challenges due to human interaction in the context of automated driving. The first work is we published in this year's in ICCPS conference. And we consider about trust-based route planning for automated vehicles. Now, I want you to think about a question. When you get to your car every day morning, and you need to choose a route, maybe drive to work, what factors do you considering when choosing a route? So this is a picture I take a screen from Google Map. So some of you can see it provides me 3 different alternative routes, balancing different factors such as distance, travel time, and traffic conditions. We argue that for automated vehicles, we need to consider, in addition to these factors, we also need to consider drivers' trust on the automated vehicle's capability. For example, if I don't really trust the automated vehicle's ability to handle urban street, maybe with lots of pedestrians, then I probably will prefer a longer distance route, maybe through the highway, but there is no pedestrian. So with that insight, we started this work. And here, what exactly do we mean trust? Here we follow the classical notion of trust in automation, which views human trust as delegation of responsibility of actions to the automation and humans' willingness to accept risk or possible harms, while the decision, the decision to delegate to the automation. So imagine if you're sitting in this Tesla's car as driver, and the road condition, as we see, is not very ideal, right? So do you trust your car enough to let it stay in the autopilot mode, or do you want to take over control? So this is a kind of measure of indication of your trust of the automation at this point. So this picture is taken from one of the survey papers about what are the factors that may influence trust in automation. You can see there are many factors that would influence trust. I don't expect you to read all the details, but the takeaway message I want you to have here is trust is a dynamic value that evolves over time during the interaction. So you can see everyone comes here initially would have an initial trust, maybe based on your pre-existing knowledge about the automation. However, during your interaction with the automation system, the trust evolves based on your interaction experience. So drawing all these insights, we kind of did an online user study via Amazon Mechanic Turk. We're trying to estimate, collect some data to estimate what are the trust dynamic models. So initially, we ask all the participants, once they start our study, we ask them an initial trust value to rate in from 1 to 7. What is their trust level of automated vehicles in general? And then we show them a video where ask participants to imagine you are sitting in the driver's seat and now your car is now approaching an incident. In this case, you can see the car is now approaching a truck in front of the lane. Then we ask the driver, do you want to take over or not? We pause the video, we ask them, at this point, do you want to take over or not? And depending on the participants' response, they may choose to stay as autopilot mode, or they may choose switch to manual driving. And because it's, of course, it's online user study, so we don't really, the participants can't really act anything. So we're just showing them different videos. If they choose manual driving, we will showing them a video of, we suppose all the manual driving will successfully do the lane changing, handle the incidents. However, if they choose autopilot, then with certain probability, it may be successful, like the video I just showed you, but with certain probability, it may crash. And after that, we ask the user, now, do you want to update your trust values? Does the experience you just had change your trust value about the automated vehicle? So we showed a series of different videos to the participants with different type of incidents. Actually, more specifically, it's 3 types of incidents. One is that I just showed you, it's there's a truck in front of the lane, so you have to do lane changing. The other one is a pedestrian is crossing a road and the vehicle need to stop and wait. And then the other one is there is an oncoming truck from the other lane. So using the data we collected from user study, we were able to estimate a data-driven trust dynamic model as a linear Gaussian system. So the figure I'm showing here is the probabilistic matrix that we obtained from using our data-driven model. So you can see trust is depends on whether the human decide to take over or not, and it depends on what is the type of the road incidents. We can obtain different transition matrix. And you can see that when the human decide not to take over, so it decide in the autopilot mode, and if the car has handled the incident successfully, you can see the general trend is the trust will slightly change, the dynamic change will slightly lean towards the right. So that means the trust will increase. However, when the if we compare the top row and the bottom row, you can see if the human decide to take over, so it's actually human doesn't trust it enough, and so it decide to switch to manual driving. So we can see it's mostly still trust that doesn't change, it does not really have a chance to increase. So with that dynamic model we have, now we consider, can we leverage that model and do the problem that we motivated at the beginning is, can we do the route planning considering the trust? So for that, we built a partially observable Markov decision process. You can see in this graphical model here, the trust is represented an unobservable or hidden mode, because that's a human's hidden mental state. And meanwhile, we have some other variables like depends on the vehicle's capability of handling certain incidents and the vehicle's location. And here there are two actions. One is a human's action, driver's action, whether they decide to take over or not, and the vehicle's action deciding which route to choose. So we consider the map of a toy example here is a map. Suppose if you want to travel from location A to location K, and we assume that every road segment have exactly one road incident type. And based on that, and using our POMDP model here, we can compute what would be the optimum route that trying to achieve the maximum the human trust. So once we get that computed that trust-based route, we now conducted another set of user study, but this time it was in my lab using the driving simulator. So we asked the participants to sit in the driving simulator and experience the route that we just planned. So we collect a bunch of data. The blue ones are mostly the data from the vehicle, like a throttle, brake, or the data. And one thing one mention here is the user actually have the ability to press some buttons on the driving simulator to indicate the change of the trust levels. We also ask the user to wear some biometric devices like the eye tracking. So you can see the yellow dot here is eye tracking. And then bottom one, we ask the driver to wear like galvanic skin response and heart rate to measure PPG. So these are indicators of the stress levels. So overall, we conducted a user study with 22 participants, and we conduct a between subject experiments, which means we randomly split the participants. 11 of them were driving through the trust-based route that computed from POMDP model. Another 11 of them are driving through a shortest distance path, which doesn't really account for trust. And with that, we were doing some ask them some questionnaires. So I only showing one results here is this is showing the after driving survey results. In general, we found that participants who take the trust-based route have more positive response than taking the baseline. You may wondering why the Q4 here, it seems the blue one trust-based has lower score than the orange one, right? So the question 4 is actually we negate the directions of the question. So because it's saying I have concern about using the automated vehicle, so lower the score is actually the better. So this is a trick we do usually in user studies to avoid like people always select one directions. So any questions before I move to the next work? Also feel free to, maybe we can also answer questions at the end, but during the talk, I would introduce several different pieces of work. If you have any immediate questions, please feel free to unmute yourself and just ask. Okay, so if no questions, I would like to tell you a second piece of work we just published in this year's CAI conference. So we were saying in the first work, we noticed that when human doesn't trust the vehicle enough, they may want to take over. And in reality, we know right now, if we look at all the automated vehicles on road, none of them are truly level 5 autonomy level. Most of them are level 3 or level 4, which means the vehicle may issue some takeover request and ask the human to take over if the vehicle wasn't sure about its own ability to handle the incidents. However, at this point, because humans usually were engaged maybe in some non-driving related to tasks like maybe reading books or maybe using your mobile phones. So a sudden takeover request issued by the vehicle would make the driver kind of surprised or maybe not ready to actually take over. So with that in mind, we're thinking, is there a way that we can, using all the data we collected about driver, to predict what the driver's takeover behavior would be before we even issue some alarms for them to take over? So that's the main idea of this work. We use all the data that we collected, including pre-driving survey and all the vehicle data, including the lane position, the steering angle, throttle, and brake, what non-driving related tasks the driver is doing, and their biometric data. We collect all the data and then we put into a neural network. It can help us to predict the driver's intention, whether they're going to take over or not. Suppose if now there's a takeover alarm for takeover request, and takeover time means how long it would take the driver to actually take over from when the time that the alarm is issued to when they actually kind of take the control of the steering wheel. And finally, the takeover quality. So if the human take over, how good is their takeover quality? Because sometimes when you are take over in a surprise and you may kind of, if you suppose it's lane changing or something, then it may not necessarily good. And with the, we did a user study. We recruited 20 subjects to come to our driving simulator lab. And we asked them to wear all these biometric devices. We did 3 trials of the study plus a baseline. So for each trial, we designed different scenarios, these 4 different scenarios that the participants may encounter on road. And we also instruct users to do 4 different types of non-driving related tasks during the trial. For each trial, we designed 15 takeover requests, including 6 true alarms, which means there are indeed some road incidents that need the human's attention. 6 false alarms, which means there's nothing going on road, but the alarm still issues. Because sometimes if too much false alarms, it may cause alarm fatigue or may actually decrease the human's trust. And 3 are no alarms, so which means there are actually some road incidents, but the alarm didn't sound. So in total, we have 15 TORs for each trial and 3 trials. So we can, for each participant, we collected 45 segments of data about alarms. And using this data, we compared the performance of our neural network-based prediction framework, which we call deep take, and 6 other classical machine learning techniques. We found out that our deep take framework outperforms all the other 6 methods in terms of both prediction accuracy and F1 scores. And these are the results of the rock clumps. And the fonts are very small to read, but you can, it's basically all the left top corner, the red ones are our deep take results. Again, it's outperform all the other method. And this is the confusion matrix. So we envision that our framework like deep take can be maybe integrated in the future automated vehicles so that the automated system can predict or can make optimum decisions based on the predicted driver takeover behavior. For example, if my prediction says that the driver's takeover time is high, which means it maybe takes longer time for driver to take over. And meanwhile, the takeover quality is low. Then in that case, maybe my automated system want to take some early warnings to improve the driver's awareness and maybe ask the driver to engage less in non-driving related tasks at that point. Okay, so for that, we conclude the part just to show you two different works we use to address the challenge of human interactions related CPS, safety and trustworthiness issues. Now I want to switch the topic a little bit and tell you our recent effort of addressing the safety challenges due to AI-enabled CPS. So the first piece of work I want to talk about is safe reinforcement learning by Shielding. We know that MARL algorithm has now been increasingly used in many cooperative AI applications like multiple robot coordinations. However, the current MARL algorithm mostly are, they do not consider safety guarantees. But we know that for some safety applications, during the MARL algorithms training process, we know the agent will do exploration. It's very important to guarantee that they do not take unsafe actions because you may even break the robot, right? So that can lead to catastrophic outcomes. So this work, we're trying to address this gap by proposing a method we call it shielding, to guarantee the safety properties over both the training and execution of multi-agent reinforcement learning. So idea is that we don't change how the reinforcement learning algorithm works, but instead, we know when usually the reinforcement learning will interact with the agent environment by proposing an action, and the environment will send back states and rewards. In this case, we use a shield to intercept the action proposed by the agent. And the shield will decide if it's a safe action, then shield will just pass it to the environment and the learning just goes as usual. However, if the shield found that the action is unsafe, the shield would replace it with a safe action. And meanwhile, we want the agent to learn, so the shield will also send a punishment back to the agent. Agent will know that this is unsafe action, I'm not going to propose it maybe next time. So with you may wondering, how does this shield magically make this work, right? So let me show you a simple example. We actually automatically construct this kind of shield by solving a safety game. Let's consider a very simple example here. I have blue and orange agents. They are moving in a corridor here. And we want our safety property is to avoid a collision. Okay, so we put it into a formal method called the slugs. It's a linear temporal logic enabled reactive synthesis. And we can synthesize a shield is now represented as an automata showing in the right. So in this automata, the safe state is Q0. And if any of the action happens, here it's lead to an error state. And here D represents the distance between these two agents. And then in this setting, in the current position shown in the figure, D is equal to -1. And you can see in this position, if my my blue agent stay wait and my orange agent move left, then it will cause a collision. So if that's the case, we would go to an error state, which means this is unsafe. Okay, so one issue about this problem is as you can imagine, because this showed do encode the joint action of all agents. So if you have many agents, then the showed, since the computational cost of synthesize the showed will kind of grow exponentially. So we propose a second approach in the same work, is we call it a factored shielding. So the idea is now, instead of using a centralized shielding to monitor the joint of action of all agents, now we use multiple shields, and they are coordinating together to monitor the set of agents together. So this approach can help to improve the scalability of the entire shielding method. So the benefits of our approach is because we didn't change how the MARL algorithms inner working. So our shielding can be posed on independent of the MARL algorithm. So we can work with different MARL algorithm. So in the evaluation side, we take different MARL algorithm. The first one is we use the CQ learning. And we tested on 4 different grid worlds. From the results, we can see that for these 4 different examples, adding the shielding doesn't compromise the learning performance. We can all converge and you get a similar mean accumulative reward per episode with or without shielding. But the table shows us very nice results that with using the shielding, either centralized or factored shielding, we can guarantee that there is 0 collision. While if we don't use shielding, we cannot guarantee 0 collision during the training process. We also tested our method with MADTPG, that's a different MARL algorithm. And with this, we're using, now you can see in these 2 examples, we actually have 4 agents. So that's more agents than in the previous examples. And for this, unfortunately, CQ learning doesn't work, or centralized shielding doesn't work. So we use the factored shielding, and it's more scalable than the centralized shielding. However, we get similar results as previously, that we can guarantee 0 collision while the learning performance doesn't compromise. Okay, so now I want to switch the gear a little bit to tell you a different type of work. We're also doing AI-enabled CPS. So we consider now the problem of predictive monitoring. So what do we mean by predictive monitoring? That basically means you want to make predictions about the future states of cyber-physical systems, and then you monitor if the predicted states would satisfy or violate certain requirement. So some examples, we can see predictive monitoring can be very promising into the decision support of cyber-physical system. Some examples we can see, like if we predict there will be a traffic congestion, then you may want to adapt to your traffic control system, right? Or if you predict that the a potential dangerous glycemia condition is predicted for the patient, then we probably will reduce the automated insulin delivery system. So the issue of the existing work in predictive monitoring for cyber-physical system is mostly they're focused on using temporal logic to monitoring individual predictions rather than sequential predictions. So the novelty of our work is that we develop an approach to monitor sequential predictions generated from Bayesian RNNs. Now, let me first motivate the problem a little bit, like why we consider Bayesian RNNs. The reason is that before that work, we actually did some study of real-world data set. So we consider 2 different data sets from sensing. One is air quality sensing data, another is traffic volume data. And we observed that in both data sets, there are significant uncertainties in the data. So the picture showing here is in 3 different air quality monitor stations, the data we collect. Even if the first 5 hours of the data have the same prefix, we notice that there are significant uncertainties in their suffix. So here the blue shaded means the entire range of the possible data, while the darker blue ones means the 95 percentile. So this is kind of expected because we know in sensing in the cyber-physical systems data, they do exhibit significant uncertainties. Perhaps it's due to sensing noise. It also could be because of environment factors like different weathers in different stations, or there could be in some other application domains, it could be because of human behaviors. So now the question is, how can we what are the implications of embedding these uncertainties into the predictive monitoring? So first, let's consider a simple example. Let's suppose now I want to monitor air quality and might have a requirement saying the air quality index should never exceed 100. If we use traditional, like say, recurrent neural network technique, it's deterministic, which means if you give it a fixed prefix like the black one, no matter how many times you run it, you always get the same prediction. That's the orange one because it's deterministic prediction. Now, let's suppose, say, if you look at this point, suppose the orange one is my prediction results, and at T3, the AQI is 102. Now, you know, this is actually violate my requirement here, right? But then what does it mean for, suppose if you are the city decision maker, what should you do about this result? The requirement is violated, but we know this is predicted by some deep learning framework model, right? So how certain you are about this prediction? So with that insight, we leverage the recent results in uncertainty in deep learning, and we train the model in Bayesian and RNN. So the idea is that at the testing phase, instead of just using the trained model directly, we would apply a dropout to the network. And then with the same input, we will get a different predicted sequence each time. And using Monte Carlo approach, if we apply it to n times, at every time step, we would get a Gaussian distribution of the predictions. So that if we now, instead of I give it a black, just to get a single orange choose, now we actually get something we call it flow pipe. So it's the blue dashed lines represent the 95 percentile of the Gaussian distribution at each time point. So within this, we call it, it's like a tube. And within this, you can have infinite number of sequences, prediction sequences. Now the question is, how can we monitor a flow pipe like this using signal temporal logic, using the traditional logic? The traditional signal temporal logic can only be used to monitor a single trace. But if you have an infinite number of traces, then that means you need to apply to infinite times. That doesn't work. So how can we monitor a flow pipe, this kind of with uncertainty more efficiently? So this is the framework we developed. We call it an STLU framework. So the real U represent uncertainty. We get the flow pipe from the Bayesian RNN prediction model, and we call it a new logic STLU. So it can specify things requirement like, with 95 confidence level, the predicted AQI in the next 4 hours should be always below 100. And sometimes, so with this requirement, we define two different semantics. We call it strong or weak semantics. So that's strong means that your entire flow pipe would satisfy this requirement. And weak satisfaction means partial of your flow pipe would satisfy the requirement. And sometimes as the system designer, we probably don't know what is the right confidence level to use. And in that case, we also have algorithm to compute the confidence levels. And so that can give us different monitoring results. And another contribution we have in this paper is now using the monitoring results, we can use it to feedback to our training of the Bayesian RL models for uncertainty scheme selection and tuning. So let me explain a little more what do we mean by this. So we know that in RL model, there are different type of dropout techniques, like some of the examples, 4 examples are shown here. And even if I select one particular dropout technique, there are parameters that we can set. The current techniques in to estimate uncertainty in deep learning is usually people would select the best dropout techniques and the parameters in order to achieve the best accuracy. However, that doesn't really consider, for our application purpose, we want to monitor the satisfaction of the prediction of the requirement. So for that, we propose a new criteria. We call it STLU-based criteria. So the intuition is that the predicted flow path should have the same monitoring results as the target trace. So we define new loss functions based on our STLU monitoring results, and we use this loss function and we put it back to the Bayesian RL training to guide the selection of dropout techniques and parameters. So this is, there are many results on the paper, but here just showing one slide. We compare the effectiveness of predictive monitoring using our technique, our STLU monitor, versus there's no monitor, or there are single, like without uncertainty, you can use some traditional STL monitor. And we evaluated in a simulated New York City data, and we can see that in the simulated experiments, we can say using the predictive monitoring, we can improve both the safety and the performance in this simulated city. Okay, so lastly, I want to tell you about our work in to address the large-scale challenges. Again, I want to use smart cities as a motivating example. In a smart city, there could be thousands or hundreds of sensors and actuators. So if we want to apply the formal logic-based monitoring algorithm to it, then 2 challenges we have to address. First one is, how do we specify real city requirement? And second one is, if we have thousands of hundreds of sensors, how can we monitor this kind of large scale sensing data simultaneously? So to answer the first challenge, we did a study we collected 1,000 city requirements from the 75 real cities around the world. And my students annotated the key elements of these requirements. We found out that a lot of these requirements are about spatial. So for example, these purple ones, they means like probably you care about some energy per 1 square feet of some areas. And a lot of them are about aggregation of some quantities. So in the current, using traditional signal temporal logic, you can't really express these kind of properties like spatial or aggregation. So we extend the signal temporal logic with 2 new operators about spatial and aggregation. Let me, I know not all of you are familiar with formal logic, so let me just briefly introduce what are the intuition behind that. So suppose we are in, let's say this is a map, and traditionally you maybe get a 1 sensor point. So that's a blue one, and you may just monitor the time series data you collect in that single location. And let's say if I care about 500 meters around the park, so that's actually cover multiple sensing point, right? So how can you do it? Let's say if I have a requirement about that, so then you probably will need to apply for each of the sensing node and each of them using STL to monitor them separately. So that doesn't really scale. With our spatial aggregation STL logic, now we can having 1 requirement, and you can express maybe within the bus area or within the school area, and the distance is within certain range, and you are going to counting maybe all locations or maybe some of the locations would satisfy certain requirement. So we did some coverage analysis within the 1,000 requirement, city requirement that we studied. Within our new logic, which we call it SaSTL, we can express 95% of them. And these two are some spatial variant, earlier work of spatial variant of STL. They also have some spatial operators, but they doesn't really consider the aggregation or counting or percentage. And compared to if you use traditional signal temporal logic, that's percentage be able to express the number of requirements it can express is even lower. So that shows you the benefits of expressiveness of our new logic. And you may wonder, okay, so not everyone is formal methods experts, and it's really a learning curve to learn how to write formal logic. So don't worry, we developed a tool. If it's a smart city applications, we developed a tool that can give you some template, some structured language template. So you only need to fill in these key elements, and the requirement will be just synthesized automatically, and then you can choose. So in this case, I can maybe, suppose I'm a city decision maker, I will choose that's my city's map, and I'm interested in some areas, maybe schools, and I was putting the data, I set the requirement, and it will show me this is actually a map taken from the Array of Things project in Chicago. So all these actually points, blue ones and the red ones, they're actually the sensing points available. And we will now getting some results. And if we have, like, say, multiple requirements that we want to check at the same time, so then there may be some trade-offs of different requirements are satisfied. And we applied these two to really large-scale real city data. One is using the data from the Chicago Array of Things collected over a little over 2 years' time. Another experiments platform is based on the simulated New York City, and you can see it's really large-scale sensing data that we can monitor at the same time. And what I didn't put in the slides here is our monitor algorithm used some clever tricks, including like parallelization and others, to speed up that you can monitor one requirement for tens of thousands of sensing streaming data simultaneously. And I'm not going to show you all the results, but let me give you one example to help you understand the implication or the usefulness of these kind of tools. Now, suppose if I have a requirement saying the average air quality within 5 kilometers of all parks should always be above moderator in the next 3 hours. And if you are curious, the next line is how the formal logic would look like. But again, you are not required to write them directly. You can use our language template to generate it automatically. And let's say the left side is the results showing you that the monitor results given this requirement. And here we randomly from the data we have with like 30 days of workday data and 30 days of weekend data. And we calculate the percentage of the days that they would satisfy the requirement. And we can see in general, we found in the work days, during the morning and before the 2 p.m. time, we found out the air quality is generally not so good. So based on these monitor results, you probably will give a message to city managers, say, try to take actions to reduce the air pollution near the park from 7 a.m. to 2 p.m. during the weekdays. Or if you are the everyday citizens, perhaps we can give a message, say, don't take a walk during the park around noon or weekdays because the air quality wasn't good. Okay, so just to summarize, in this talk, I briefly tell you our recent work in trying to address the challenges in assuring the CPS safety and trustworthiness in terms of human interaction and AI enabled and large scale challenges. So you may wonder what's next. So there are several different works ongoing in my group. And one of the work I'm very excited about is we just started a new NSF project it's also a new NSF program called Designing Accountable Software Systems. So in this project, I'm collaborating with a law school professor, and we're trying to both bring the legal aspects into accounting the software accountability for safety critical applications. And meanwhile, we want to use the results from software design like formal verification to inform how the regulators like FDA and other and NISA, how should they regulate like medical devices or self-driving cars. So let me give you one example. In the right, you can see a picture of integrated medical device for diabetes treatment. So the patient is wearing a continuous glucose monitoring sensor and also an insulin pump, which are controlled by some app maybe installed in a mobile phone. And so this is an integrated system. However, right now, FDA have to regulate each of these devices separately rather than consider them together as a connected system. And another challenge is, some of the sensings and control apps are now using machine learning based algorithm. That's posed significant challenging to the regulatory challenges. So part of our project's goal is we're trying to see what kind of solutions we can provide to both guarantee safety and inform the regulatory challenges. Okay, so I would want to acknowledge all my students and my collaborators, and these are some of the work that I mentioned in this talk. So now I'm ready to thank you, and I'm ready to take questions.
Thank you so much for that wonderful presentation. Do we have any questions from the audience? So we have a question from the audience requesting more information about the factor shielding and how it works, if you could provide more details.
Okay, yeah, the factored shielding is used for scalability. Okay, let me go back to the slides of the factored shielding. So I wonder, the audience who asked the question, I'm wondering, is your question about how the factored shielding can work with the integrate in this framework, or how do we synthesize the factored shielding? So maybe I can briefly talk about both. So here, the factored shielding is if we have multiple agents, we're trying to decompose their actions. Let's say if you have 4 different agents in a grid map, we would decompose it into different areas, and we know each area will be responsible for one of the shield. And the shield synthesis is the same as centralized shield. We still get the shield by solving a safety game, but because now each shield is only responsible for a subset of the joint action instead of all of the agent's action. So the shield synthesis is much more scalable, because as we said before, one of the major challenges is when we were trying to do the safety game, you have to consider for the centralized shielding, you have to consider joint action of all the agents, and it's going to explode exponentially. But now, because each of my shield only consider a subset of the agent instead of all the agents, so it's much attractable than a centralized shielding. And now with the shielding, so each of the shield will work on its own. They will just look at the actions that they are responsible, decide whether they are safe or not. And the reason that we need coordination is because sometimes the agent may move in, they may leave one shield and enter another shield. And in that case, we would need some coordination. So does that answer the question? Okay.
I believe it did. Thank you so much for that question. Any other questions from the audience? We have a bit of time. Well, if not, I want to thank the speaker again, Professor Feng. Thank you for the wonderful presentation, and thank you to the attendees for joining us. We are off next week because of the academic recess, but we will have other seminars in the coming Friday. So please join us once again. Thank you again, Professor Feng, and thank you, everybody.
Yeah, thank you for inviting me. It's a pleasure to be here.